Good, nice. And Ryan's going to talk to us about LiDAR scanners for continuous beach morphology observations.
So can I just get a confirmation that you can hear me over there?
We can hear you, yes.
Okay, fantastic. So
thank you.
In front of you, what I think we're looking at, though sometimes video does not work so well, and PowerPoint was a sort of time lapse of the field site where we did a deployment earlier this year on the Outer Banks to test out some new LiDAR scanning technology during storm impact. And I don't think the video is playing, but let's see if I can at least advance. Here we are. It probably doesn't look as good over Zoom. I'm sure it's quite jumpy, but rest assured, what we're seeing here is a wave run up during high tide, which is impacting a dune, or what I like to call an air quotes dune / dike system in front of this house here. So I'll just talk today about a deployment we did on this particular house and in this particular region as sort of a miniature small scale test of some pretty cool new 3D LiDAR scanning technology. So the reason we chose this particular field site, which is denoted here in the red circle along the Outer Banks, was because this stretch of coast is eroding quite rapidly. In this circled area, the field site was located in Rodanthe, North Carolina. The average, latest average yearly annual erosion rate is about 5.5 feet per year. But over the past couple of decades, that has been accelerating from about 20 years ago, being about 2 feet per year. As most of you probably know, overwash is a common thing that occurs along this stretch of a highway, particularly the S-curves on NC-12. And so recently the Jug Handle Bridge, as it's called, right, has been open to bypass this overwashing region. So that may have more significant impacts down the beach. So there was a storm that was forecast to approach and pass near the Outer Banks of North Carolina, as indicated by this forecast screenshot showing a forecast predicted simulated radar. And so it was going to be a pretty large low pressure system. So the Nearshore Extreme Event Reconnaissance or NEAR Association decided to deploy a field mission, and the Weather Channel termed this Winter Storm Keenan. Our report for this and our preliminary data report and uploaded data, it can be found on the Natural Hazards Engineering Research Infrastructure online portal. This is a picture a few days prior to storm impact. Here we can see a pretty steep beach and a scarp here, as well as a dune or dike scarp, which existed from a prior storm about 2 months before this study. This is, again, the region. Showing here some forecast water levels. So there was about 2 days predicted of higher water levels, not quite necessarily up to what was predicted to be the elevation of the dune in that area. So it was going to be an interesting storm to investigate, because it was not expected to be major overwash, but perhaps there would still be lots of coastal erosion. We also looked at a lot of the data from a lot of sensors around the region to get sort of a larger macro scale view of just how the entire region was being impacted. So these are some water level observations. I just want to put into context here sort of what this region of the coast, right, had been experiencing throughout January and February of this year. So these are plots of water levels from 3 different stations along the coast. 1 is oceanside and 2 are more sound side, so to speak. And here are 3 events where there was a pretty significant, say, offshore storm impacts in the month of January. And then here I've highlighted Winter Storm Keenan. So we see over the month of January, particularly on the sound side locations, the water levels were almost always higher than the forecasted water levels being blue, measured being green. If we take a look also at some of the wave data at this buoy and the wind and meteorological data from this station near Oregon Inlet, where our field site is sort of right between those 2 stations, we see that these 3 storm events consisted of about 30 to 40 mile per hour gusts, knots of gust, and about 25 to 35 knot sustained wind speed. And it's notable that these 2 in particular occurred right before Winter Storm Keenan. So this area was already really vulnerable because there was large waves, almost 20 feet in significant wave height, just about a week or 2 prior to Winter Storm Keenan impacting this area. I also just want to point out the wind direction here. So here during the large events in the middle of January, with the largest wave heights, we see the wind direction coming around that time out of the east, which would be onshore. Whereas during Winter Storm Keenan, for the most part, the wind speeds were from the north. So sort of from north to south in the longshore direction. So here is our deployment schematic. It was quite an extensive deployment. I'm only going to focus today mostly on LiDAR data, but we installed 2 LiDAR scanners on this house here, some pressure gauges on the pier to measure waves and water levels. We also had cameras 1, 2, and 3 monitoring in real time the impacts to the area, and a water level sensor here installed on this house. Here's a picture of the wave gauge installed on the pier. And then this is one of the 2 LiDAR scanners that was mounted on the deck on the house south adjacent to the pier. This is just the wave and water level data that was recorded by the RBR Solo D wave gauges. And so in the future, we will process this data to sort of time correlate the impacts in coastal erosion from the morphodynamics and tie that into the hydrodynamics. However, for the sake of time in this presentation, I will not cover any of those details further. We captured the morphodynamics of the beach in this particular area using 2 compact, low-cost 3D LiDAR scanners. This is the Blickfeld Cube 1 model. They're about $5,000 each. I just mentioned that because that's relatively inexpensive compared to some of the LiDAR scanners in the hundreds of thousands of dollar range. They're also really cool because they can be logged autonomously. And so we just run Python code or some other API scripts to log the data and control the sensors continuously. So we captured high resolution scans every 4 minutes for about 3.5 days, which consisted of before, during, and after the storm. We would have had 2 weeks of data, but I made a silly mistake and bought cheap USB drives that I thought were 2 terabytes, and turned out they were about 8 gigabytes. So we ran out of data after about 3 days. So this is just a picture of the setup that we had on the thing. Of course, there was a lid over this. And so I'm going to focus on analysis just on L1 today, which was on this corner of the house. But this just gives you a quick sort of overview or picture of what the data kind of looked like before I jump into data analysis. And so here is the pool wall looking out over the deck. And then in the LiDAR scans here, if you look closely, perhaps you can sort of see the outline of this pool wall there. And so this is what we're capturing with those 2 LiDAR scanners. And so we get this high resolution field of view every 4 minutes. We get a scan like this. But by the way, it only takes about 10 seconds to complete this entire scan. And then this is what the beach looked like after the storm. So we need to georectify the data. So in order to do that, we installed or laid out 6 ground control point targets, which look like these little white cylinders here, and across and throughout the field of view of the LiDAR scanners. And then we survey those with RTK GPS, and then we can georectify the XYZ point cloud data into state plane coordinate systems. And then we need to validate whether or not our georectification was actually done appropriately. And so we also took, after the storm, 7 post-storm beach profile transects. We ran out of time to do those pre-storm, but we still have the pre-storm LiDAR data. And so then what I'm going to show you today is a sort of just an overall comparison of how did the survey data and georectified LiDAR data compare with each other. By the way, it was very cold, as you can see by these images here during this rapid response. So we carry out this sort of sequence of filtering. So we filter the LiDAR point clouds. We have to remove the waves, water, non-land objects like people, fence posts, and birds. And so while you did see this very nice large triangular field of view from the previous slides of the LiDAR point clouds, we end up removing a lot of that data to just give us the actual dry beach. We also removed the SCARP from beach profile surveys as it was not so reliable. And then we removed the dune, as I call it, the air quote dune, from the LiDAR point clouds, as well as anything landward of the dune. Then we just interpolate the LiDAR data and the beach profile survey data onto the same grid with about a half-meter grid spacing, dx, dy. And then we use inverse distance squared method to give us an interpolated grid. So this just shows you sort of a 3D view of the beach profile transects that we measured, and then the L1 LiDAR field of view. with the magenta dots are the filtered point cloud data. And then here is our LiDAR surface. The interpolated survey surface is not pictured here, but would overlap across this entire span. So then we're going to look at transect 4 here to see how well the LiDAR data compare with the surveyed grid, interpolated grid. So on the top, what you're looking at here is on the x-axis, you have cross-shore coordinate, and on the y-axis is the long-shore coordinate. So we're looking from above, and here is the region where the LiDAR and survey data overlap with each other. And this is transect 4 again, just to orient you. So offshore is over here to the right. So this is just a difference map of the overlapping survey and LiDAR interpolated grid. And across this entire region, we have an average root mean square error of about 7 centimeters and a mean bias of about -5. So that's just the difference between the LiDAR and the survey. Now, if we look just at transect 4, which is plotted here on the bottom, now in profile view, and we evaluate the statistics just in the region or the span where we have LiDAR data overlapping with survey data, we have an improved average root mean, an improved root mean square error of about 4 centimeters and a mean bias of around 3.5 negative centimeters. So I think that's relatively good given that the overall error between the two different survey methods, vertical error is in the range of a couple of centimeters. And I just want to wrap it up and end here. We've been now working on analyzing the filtered data, but prior to that, I did make an animation of the unfiltered gridded surfaces. So here you do see a bunch of noise from the waves coming in, but there was the erosion of the beach profile during storm impact. And then during the next high tide, we see some accretion here. And then the next higher high tide, we see additional erosion and landward transgression of the beach profile. Those were some people walking through the scan that we had not filtered out yet. And then if we take transect 4 and look at the time stack, what we can start to see is with this kind of data sets and with this technology, of course, this is just 3.5 days. You can imagine here we see 1, 2, 3, 4, 5, 6 high tides coming into our field of view. We also see this rapid landward transgression and erosion of the beach profile and the scarp. And then during the next higher high tide, again, we see a little bit more erosion. And this grid, each grid is 0.5 meter. So there was only 1 meter remaining of this dune before the pool wall at that particular home was going to be impacted by waves. So this is a 3-dimensional view of that same time sec, just to give you a sense of what we're able to resolve. And if you look here after the second higher high tide, where the additional erosion occurred, you can see in subsequent high tides, slight accretion on the beach, just at the landward edge of the beach. Of course, this was sort of the beginning of what became accretion over time. And if we look at images that I took in the end of February versus the end of August, both photos were taken at low tide. Here we see people way out in the ocean, so it's quite shallow that far out, versus here, which was a couple of weeks after the first house of what became 3 houses that collapsed. And so there was quite a significant difference. It doesn't look like this today, however. And so I would love to, moving in the future, try to apply this technology to more continuously monitor beach morphodynamics over more than just 3 days, because as we all know, the beach is a very dynamic system. So thank you, and I will take any questions.
Ryan, you did an excellent job on your time, and you've got 7 minutes for questions. So we have a mic set up back here, but I'm going to bring this to Barbara Dahl so that she can ask her question.
Ryan, I'm wondering if it would be good to just maybe have like a summer snapshot and then a winter snapshot on a non-storm day, and kind of look at this over time, because it seems like you're going to generate a massive amount of data. So like if you have continuous over time, I'm just kind of thinking of what the application of this would be and how to do it like practically.
That's a great question. And I think part of the initial goal of this was really just to prove the concept and prove the sort of methodology and analysis methods. But moving forward, the fantastic thing about this particular scanner model is that it's very, very configurable. And so depending on what you're interested in, if you're interested in just a single transect, you can program it just to conduct a scan along a single transect. You can also program it to do a scan once a day, once a week, once per hour. Or you can even remotely talk to it and say set it to do a scan every hour or once a day at low tide. But if this storm is coming, then you can reprogram it to start scanning once per hour, once every 30 minutes. And so there's a ton of flexibility because sure, if you're scanning every 4 minutes for an entire year, it does become quite an extensive data set. But yeah, does that maybe hopefully kind of answer your question? So I think there is tons of room for like practical applications. It comes down to having partners who have power supply.
She said that did answer her question. We have plenty of time for questions too. We have to wait until we get to like the 20-minute mark before our next speaker goes.
Yeah, right. This is Lin. I'm from Coastal Studies Institute, and we are also using LiDAR. And we have ground-based LiDAR from Regal. It's called VZ400i. So first, for those LiDAR sensors you use, what's the range limit? I see it's a short profile. So what's the range limit for your LiDAR sensor?
That's always a loaded question, right? So the manufacturer states a range of 250 meters, but that's rarely the case, particularly when you're outdoors in sand and water. A student of mine has also, this past summer at the FRF, tested the entire summer, different configurations on one of their LiDAR towers. And I think during low tides, there was a range out to about 50 to 75 meters. It's a little bit less dense at that point, but the actual point cloud on this particular slide, if I can get over it, would kind of come back out and then sort of connect over here. But it just doesn't get any return off of the non-white water that far away. So here it's around 25 to 30 meters in the cross short. But that's the reason you're only seeing that is because the water at this particular location was only 25 meters away from this person's house. But I think up to maybe 75 meters is what we've seen at the FRF.
Okay, yeah, thank you.
And you can even go to the website of Blickfeld, and there are a couple other graphics and figures on a case study that I did with them, which shows some graphics from the FRF, which will give you maybe a better visual sense.
Yes, thank you. But I have another question. Can I ask?
Let's see if there's another. Are there any other questions? You can ask one more.
Okay. Yeah. So since you are also curious about the accuracy of those LiDAR sensors, I'm also interested in like we can bring our Regal VZ400i and scan the same area and let's see how does it work. What's the what does the result look like? Because we also have a very interesting site in Rodancy, it's in north part of Rodancy. There is a very frequently overwatched area. We bring our scanner to scan those overwatched area again and again. So
I think so. Over this summer at the FRF, maybe you're aware that they have, I don't remember the model, of Regal LiDAR scanner that does a full scan across the entire FRF. They have multiple. And so part of that study was also to look at how accurate this model was in georectification versus the previous model. We're still improving the georectification methods. Right now, we're just using a sort of camera-based rectification approach. And skipping the intrinsics. So we just calibrate for extrinsics. But I'm sure there are better approaches to improve the accuracy as far as, point cloud registration and all this other kind of stuff. But certainly more comparison data sets between this model and other models in all sorts of different environments would be a good idea.
All right, thank you so much. Yes, hi, I am Logan Howard. I am a senior undergraduate at the University of Nebraska in Lincoln. But this was a research project I conducted as a part of my Noah Hollings internship at the Weather Forecasting Office in Newport, Morehead City, North Carolina. So first, to start with a little bit of background. So for weather models, currently, they are ingesting sea surface temperature grids that are of very coarse resolution. And that is of particular importance here in North Carolina because just off our coast, we have the confluence of the cold Labrador current and the warm Gulf Stream current that creates a very sharp sea surface temperature gradient that the models are not capturing effectively. This gradient is particularly enhanced in the cold season. And here I have an example from February, where we can see that just off our coast in the marine zones here, that there is a nearly 30-degree Fahrenheit temperature difference across a distance of just 60 miles. And this is pretty significant. And another thing to note is that this is of particular uniqueness to the Newport region, which I have here in the black squares. So right in our region is where we have the confluence of these two ocean currents. So the objectives of this project was, the overall goal was to help improve our marine wind forecasting. And of course, that will help improve our marine hazards like small craft advisories and gale warnings, as well as eventually improving our wave and rip current forecasts. And the way this will be done is we built a tool that will incorporate winds and sea surface temperature observations to help correct and make better marine wind forecasts. What this means scientifically is that we are going to determine how well winds are mixing in the marine boundary layer. And just for context, the boundary layer is the lowest, approximately 1 to 2 kilometers in the atmosphere. And this is the region where the winds are under the influence of the friction by the surface. So in it, we have mixing that's occurring throughout the day, and we can approximate this based on the lapse rate, which is the rate of change of temperature in this layer, by using the sea surface temperature and the temperature at the top of the boundary layer. So we will catalog all these relationships and any additional variability by other things and put that into a climatological catalog that is put into this tool. So quickly going back to the sea surface temperature maps, here on the left, I have an example of a sea surface temperature grid that is being input into a weather model. And on the right, I have observed sea surface temperature, which is a blend of buoy observations and remote sensing satellite observations. So the first and most important thing that you can see is that the gradient is much larger and spans a much larger space than what was observed. Another thing to note is that the sounds are actually 10 degrees warmer in the model than it was in observations, and that's going to have a big impact. One last thing to note is that the bays, Onslow Bay, these are really shallow continental shelf waters, and thus these waters are a little more influenced by seasonal variability. And thus you can see in the model, they're just a touch warmer than what was observed. And one last thing to note is that this is one example from one weather model, but all high-res American models are using a sea surface temperature grid that is of this quality or similar. So this problem is not unique to just one weather model. So the observations that were collected, we took sea surface temperature and as well as surface wind observations from 2 buoys, Diamond Shoals, which is located just off the coast of Cape Hatteras, and also Onslow Bay to the south. And this was obtained from the National Data Buoy Center. And characteristics from aloft were taken from radiosonde soundings. Those are occurring twice a day at the Newport Weather Service Office, which is located in blue. And this data is stored in an archive on the Iowa Environmental Mesonet website. Data was collected over a span of 4 years. And if any sounding or buoy data was missing, the entire time slot was scrapped just to make this easier to work with. And while we did have to remove quite a bit of data, we still ended up with between 1,500 and 2,000 data points. And just to clarify, this does span all 4 seasons. And since soundings are taken twice a day, we have morning and evening observations. So that's twice a day. So the first thing we wanted to make sure is that there is a relationship between the wind speeds at the surface and the wind speeds aloft at the top of the boundary layer. We chose two different layers to represent different heights of the boundary layer. And what we found is that across the board, we do have a very nice, even normal distribution, which is good. That means there's a pattern to this and that this can be easily predicted. But you will note that there is a very large tail that extends out to the right here on the x-axis. And you'll see that this ends at 2.5, and that was a deliberate choice because these wind speed ratios that are very high, so 2.5 or greater, these wind speed ratios could be attributed to small scale things that were not representative of the overall flow of the atmosphere. These could be a lot of different things. These could be fronts. This could be related to storms, tropical cyclones. There are a lot of different things, but the point is that these are weather events that the tool is not designed to capture. So these instances were not used in this tool. I have a couple examples here just to illustrate. So here we can see that we have a stationary front bisecting the region. And what's important here is that the sounding location on the land is on one side of the front, while the buoys are on the other side of the front. So as you can imagine, there are major differences here in the wind speed and direction on either side of this front. And so that's gonna affect how the mixing is occurring in both of these regions. And the tool is just designed to look at the whole region, the region as a whole with similar characteristics. Here I have an example of a nor'easter. So you can see there's a lot of boundaries, a lot of fronts. We have a large cyclone occurring, and this is just not what the tool is designed to look at. So now that we have all of these wind speed ratios, we want to tie that back now to temperatures, specifically the lapse rate. So I'll explain this diagram. So on the y-axis, we have lapse rate, or the rate of change of temperature in the atmosphere. On the top, we have instances where we have an inversion, or where temperatures aloft are warmer than at the surface. And then as we go down, we are having the atmosphere increasingly cooling, or said another way, we have an increasing lapse rate. On the x-axis, we have greater wind speed ratios. So what you can think of that as is better mixing in the boundary layer. And what you can see here with these diagrams is that with an increasing lapse rate, we are seeing that mixing is getting better or more efficient in the boundary layer. And we can see that here for both of these different heights that we chose. And now here's just the same thing for the other buoy, and we have the same relationship here, where we are seeing that mixing within the marine boundary layer is becoming more efficient as our lapse rate is increasing. So with that, we wanted to see if there was any other variables that would otherwise interrupt this relationship. We looked at a couple different things. Here I have season, time of day, so separating all the morning and evening soundings. And then we also wanted to repeat this lapse rate calculation with the air surface temperature. So before we were looking at the water sea surface temperature, and this is the air temperature just above the water. And what we found is that all of these variables do not greatly affect the relationship that you saw before. They were all statistically insignificant. And also the air temperature does not change as radically as the sea surface temperature. So these relationships were not as meaningful. But one thing that we did find was important was wind direction. So we divided wind direction into two different bins representing northerly winds or cold air coming into the region and southerly winds or warm air coming into the region. And what you can see here on these graphs is that when we have cold air coming to our region, we have a greater spread of possible wind speed ratios. Or what we can think of this is that when we have cold air, we have an increasing chance that mixing efficiency will be increased. The way that this was incorporated into the database was that the maximum and minimum possible mixing efficiencies are going to be determined by wind direction rather than just having one set for the entire database. So now that we have all of this information, I want to take a minute to explain just how this tool is going to work and what this looks like. So the tool ingests 4 variables. We have sea surface temperature observations. We have the temperature at the top of the boundary layer. And we also have the wind, speed, and direction at the top of the boundary layer. It's just a simple subtraction to get our lapse rate. And then with that and the wind characteristics, the database will take this and look and figure out what wind speed ratios and what range goes with these variables. And so actually you don't just get 1, you actually get 5 possible wind speed ratios, 2 of which represent our lowest end possibilities, which is quantified through our 10th and 25th percentile, our most likely situation, which is also our median, and then our highest end reasonable situation, which is quantified through our 75th and 90th percentiles. It's just multiplication to get our wind speed. We reincorporate our surface wind direction to get a final wind grid, a wind forecast grid. So with these grids, the forecaster is able to pick and combine and blend these grids as they see fit. And once you have that, then you have your final wind forecast grid. Through a previously established tool called the Marine Wind Gust tool, you are also able to make a wind gust grid based on the wind grid that you just made with my tool as well. So we'll go through that one more time, actually using a couple numbers. Here's an example from January 16th, just a random day. And then on here, I have the characteristics that are being input into this tool. So once again, we have our sea surface temperature, we have our temperature and wind at the top of the boundary layer. We calculate the lapse rate, and then with that and the wind, the tool goes into this database and picks a range of wind speed ratios that, based on these observations, should approximate the amount of mixing that is occurring that day. So again, we have our 2 low-end scenarios, our most likely scenario, and then our 2 high-end scenarios. So you'll see between our 10th, 50th, and 90th percentiles, we have about 10 to 15 knots of variability on either end. And while that is a lot, we wanted to do this on purpose because as you saw in those histograms, it's a pretty decent amount of spread on both ends. And so instead of just giving you a most likely scenario, we wanted to also give you a high end and low end scenario so that based on the conditions that you're seeing, you can pick and blend and choose. And based on the current scenario, you can make a more educated guess on what you think the amount of mixing is going to occur. As I said before, the surface wind speed direction is just reincorporated, and then you have your final grids. So as I was saying before, the forecaster can pick, blend, and combine these as they see fit to get your final wind grid. Though in this day, actually going with the most likely scenario would have been a pretty good scenario, as what was observed at Diamond Shoals that day was a wind speed of 21 knots. And then using the Marine Wind Gust tool, you get your wind gust grid. And so what that would generate is a 25 knot forecast, and the actual observed value was 28 knots. So what this looks like in the computers for the forecasters to use, it is labeled the empirical marine wind tool, though this is subject to change. And when you run this, it produces the 5 wind grids that we have been talking about. So here's an example of a sea surface temperature grid that you can input. On the left, we have, again, a model, and then on the right, we have satellite-derived observations. And as you can see, the big change here is in the northern waters where we had some upwelling, and you can see that the temperatures are about 10 degrees cooler than the model thinks is occurring. So what this looks like is you just hit populate, and then it will produce these grids. Currently, it just runs, but as we make changes, we want to insert a user interface where one, you can pick which model that you are importing, as there's many different kinds. You can select the height of your boundary layer, as we studied the 2 different options. And then we want to also be able to include preset edit areas. So for example, in this day, you might only want to select the northern waters, or you might want to only select the sounds where the model is doing okay, and then where the model needs a little bit of help. So as I said before, these 5 grids will appear based on the tool that we have just discussed. And just to compare here, I have the 10th and 90th percentile values. And you can really see here where the tool is doing its magic. You can see here in the northern waters where we have slightly lower temperatures. You can see here where the tool is adjusting and producing lower wind speeds that the model would not be able to do on its own. So just to restate our results, we found that there is a normal distribution in the ratio of the wind speeds at the surface and the top of the boundary layer, and that there is a relationship with these ratios to the lapse rate in the boundary layer. And thus what this means is that we can predict mixing efficiency based on sea surface temperature observations. All these relationships were stored in a database, which was then inputted into a tool for forecasters to use in real time to create probabilistic marine grids, which they can use to forecast. I would like to thank the entire Morehead City staff for our journey and the office. A particular thank you to my mentors, Carl Barnes and Ryan Ellis. I want to thank Donnie for helping to code up the tool, and also David Glenn for the use of the Marine Wind Gust tool. I'd like to thank the Hollings Undergraduate Scholarship for providing the funding and resources for this research. And I would also like to thank Sea Grant North Carolina for hosting this research conference. I have all my references here, and if we have time, I'm available to take a couple questions.
Yes, we do have time for questions, about a little over 3 minutes. Great job with your time, great job with the energy, and for coming from Nebraska to talk to us about the Gulf. Questions?
Have you tried comparing your results with the SWAN, the one that is used in AdCirc, especially in terms of wind direction?
We have not compared these results to the SWAN model, although this is something we can do once we start operationally use with this tool. Once we get a little more into the cold season, and this tool is a little more effective, and forecasters can provide their input and see how the tool is doing.
There's anything wrong? Mike? I've been sitting all day, so this is great walking around.
Thanks, great job. I was wondering with some of the work, inland water bodies with water temperature being a signature for groundwater, but I was wondering if there's any influence you could see in the estuaries related to the amount of flow coming in, like moderating temperatures and that sort of thing.
Currently the operational use of this tool is just a little bit limited since we developed this over the summer. But once we have more use with this upcoming winter, we'll be able to see that and have a little more answers for you.
Thank you.
I just wanted to ask the question, Logan, because we know the answer, but how much marine forecasting experience did you have when you came into this internship?
Absolutely none.
So he did a lot of work over 10 weeks. We're very proud of what he was able to do. So.
Yeah, absolutely. A round of applause. Any more questions? One, okay.
What's next for you?
Yeah.
So currently I am exploring a couple grad schools, but I would eventually like to apply and join the weather service.
Really good answer. Thank you. Thank you again. So we have another friend from the National Weather Service here to talk to us, Matthew Scalora. Oh, nice. And he's going to talk to us not about new wave information, but new wave information included in the National Weather Service Coastal Waters Forecast.
Do you have a presentation? She was in there.
if we can't find it, we could switch up the order of the speakers.
This is all that I have access to. Is it possible as one in one of the
Yeah,
different
I
ones?
remember seeing those three, and mine was right next to it. They updated theirs a day, I put mine in on Sunday for the first time, and I think they had done theirs on Friday and Saturday.
I'll take responsibility for this. Did you find it? I can't find it.
No, I don't know.
Let's just switch, if you're okay with switching speakers, we'll let Krissy go and then we'll find yours, unless you
Okay.
have it on a drive.
No, I don't have it.
We'll find it.
I could send it to you from my account maybe while.
Okay, yep, let's just do a little switch, no. Krissy, it's here, there's Krissy. From the US Geological Service, another federal agency that we love, is Krissy Hopkins. Her presentation is, well, you can see the presentation title right there. Thank you, Krissy, for being adaptable.
Yeah, no worries. Great. Well, thanks everybody for sticking it out, and excited to talk to you a little bit about green stormwater infrastructure and some monitoring that we've been doing. This is actually in Maryland, but I think it is a good example of when we implement these practices across the whole watershed, what are the impacts that we see? So we don't have a lot of places where we have a really dense installation of stormwater practices like rain gardens and infiltration trenches and these types of newer stormwater practices. So I think this has some useful information that people can use along in coastal areas as well. So here's a webcam video here showing a stream in Charlotte combined with USGS stage data. So we can see, urban streams are really flashy. They rise and fall very quickly. And when we combine things like webcam data with, discrete measurements of something like stage, we can more easily visualize kind of the impact and the scale at which flooding happens in our urban areas. So what my research has been focused on is looking at comparing a few large centralized stormwater practices, so things like large retention ponds, to what happens when you install a bunch of smaller practices distributed further up in the watershed to a range of different stream functions. So I'm going to call these large centralized stormwater practices versus many small distributed stormwater management practices. So we've been looking at changes over time as an area goes from agricultural land use to suburban neighborhoods. So here's just an example of the land cover changes that we've seen in the study areas that we're working in Maryland. You can see the agricultural fields here and some of the forested areas that were converted into roadways and houses for people's neighborhoods, and then a school in the northern part of the image here. So this is in Clarksburg, Maryland, which is a suburb of Washington, D.C. We have been monitoring this area since 2004, so it's a pretty long-term study that we've been doing over a decade, and comparing control watersheds to 3 watersheds that underwent suburban development. So you can just see kind of where those watersheds are and show the watershed boundaries there, and then the diamonds indicate where USGS has been monitoring stream flow, and then the county has been monitoring a range of different functions for water quality and the benthic community within these watersheds. So I'm just going to zoom in a little bit so you can see what these watersheds look like. These are the control sites. We have a forested control site, which is the county park. These are small watersheds, so you can drive from one end to the other in about 15 minutes. You can see like a forested site here that only has about 2% impervious cover, so things like roads and parking lots, very limited here because it's a park, but it also was formerly agricultural land, so it's kind of secondary growth forest. It's hard to find anywhere in this part of the country that hasn't been disturbed in some way in the past, so it's kind of like the least disturbed area that we can find within this small study area. The second control is an urban control. So this has kind of the development style that was happening in the 1980s. So large detention ponds are kind of the primary form of stormwater management within this watershed. And then the newer development that's gone in has more of these green stormwater infrastructure practices. So there's a few big box stores that went in recently that have micro bioretention, so small rain gardens installed in the parking lots. That's what all those little purple circles are there. And then you can see the stream, and where we monitor downstream is the diamond, and then the retention ponds are shown as little diamonds in that far map there. And then the county has monitored stream cross sections in these watersheds, so that's what those little crosses are. And then the treatment watersheds, these are the ones that went from agriculture to suburban development. You can see all the stormwater practices there as the little circles. Hopefully you can see that in the image there, but they also designed the roadways to have swales rather than curb and gutters. So trying to further disconnect those impervious surfaces from the stream itself. So you can see things like dry wells that were installed behind houses. So that takes water from the rooftops and tries to infiltrate it into the ground right next to the houses. Not like directly next to the house, but close by the houses. And then some other practices. So all of these stormwater features are arranged in a treatment train. So water from one practice goes to another for sort of redundant stormwater treatment. Now this is the second watershed that underwent development. It has 44% impervious cover, so it's like pretty built out within this watershed. It's a mix of single family homes and townhouses, so a little bit denser development. And then it has almost twice the number of stormwater practices. So this is even like smaller practices, things like tree box filters, which are just look like kind of a tree, but it has a gravel area underneath the tree that provides stormwater storage and some treatment along the roadways. And then there's also things like infiltration trenches near the roadways. And then the last site that we've been monitoring, this is the one that's kind of currently finishing becoming a suburban neighborhood. So you can see some construction activities in this image here. This one has 20% impervious cover and a fewer number of stormwater practices because they're still were being built when we finished this study. And then it has a larger sort of forested buffer area. So the bottom part is still fairly forested. So what we've been doing is looking at a suite of different stream functions. We're looking at hydrology, water quality, geomorphic changes, and then changes in the benthic community itself within the stream. So I'm just going to highlight some of the main findings that we found for these 4 general categories of sort of stressors and stream functions that we've looked at. So USGS has been monitoring stream flow in these watersheds since 2004, like I said before. So we monitor flow every 5 minutes. So we've taken that entire stream flow record and identified every single storm event that happened and then matched that up with the corresponding rainfall event. And this is showing you the peak stream flow during each of those different events matched with the precipitation amount during that event. So you can see for small events, these treatment watersheds function fairly similarly to the forested watersheds. They have lower peaks than the urban control site, which is that older type of development. So for these small events, we're talking about like 10 millimeters of rain. The stormwater practices seem to be doing a pretty good job at mitigating that flow. But then as you get to larger and larger events, these practices are only designed to manage about 1 inch of rain. So you see that benefit sort of filtering off for these larger and larger storm events. But the treatment 1 watershed still has significantly lower peak flows than the urban control site, even for those large events. Even though it's not quite as good as the forested site, we still see some benefit of these practices for some of these larger rainfall events. Also compared the peak flows since these watersheds are so close to each other, we can assume that rainfall patterns are fairly similar across this area, although in the summertime that gets a little messy, but we can compare an event that happened in one of these watersheds to the other one. So each of these dots here represents one rainfall event that happened, and then the peak flows from the 2 different treatment watersheds during that event. So any dots that are above the line here indicate higher peak flows in the treatment 2 watersheds. And you can see that most of the peak flows were larger in that treatment 2 watershed than the first one. 86% of the events were higher in the treatment 2 watershed. And we can just think about the differences between these 2 watersheds. The treatment 2 watershed has like 11% more impervious cover. So there's a lot more water to manage in that watershed, which might be why those peak flows are higher, even though it has a denser, higher density of stormwater practices. So it's not just looking at, the amount of impervious cover or the number of, it's not just looking at the number of stormwater practices, but like the relative contribution of that stormwater to the number of practices that are implemented. So because there's so much more impervious cover, and these are smaller practices, they're not necessarily able to handle that amount of water. We have a little bit of nutrient data. So we've been looking at this is base flow nitrate concentrations in these streams over time. And we can see the nitrate concentrations are elevated in all of these watersheds, so like above 1 milligram per liter, because of the agricultural legacy of this area. So groundwater, get them up here. Groundwater concentrations of nitrate in this area are elevated due to the agricultural legacy. So this map here is showing just the areas where you would expect groundwater nitrate to exceed 3 milligrams per liter. But we can see that after development happens in this treatment 1 watershed, which is the blue circles here, nitrate concentrations decline by half for base flow in the stream and in the groundwater, which is the triangles there. We don't have a ton of groundwater monitoring data, but we have a little bit of groundwater data. And we can see that those concentrations have declined over time after construction has kind of ended, but they still remain fairly elevated. And even though concentrations have gone down, we've actually seen base flow in these streams go up. So the overall export of nitrate has remained above roughly the same in this watershed over time. And it still remains higher than the forested reference site and the urban control site. We've also looked at specific conductance. So this is just showing changes in specific conductance in the stream. So that's kind of like how salty the stream is. And you can see that specific conductance has increased in all of these watersheds, the treatment watersheds during development, but at different sort of rates because of the timing of when that development happened. And the urban control site has the highest specific conductance concentrations. We've also been able to look at changes in the stream itself, so the particles within the stream channel, and we can see that during construction in both the treatment 1 and treatment 2 watersheds, we see that sand and silt and clay increase during construction or after construction in these 2 watersheds, which has important implications for the habitat that the benthic community relies on. We've also looked at changes in stream cross sections. So here's just a GIF, hopefully it's working, showing changes in the stream channel itself. So the county has gone out and monitored cross sections within these watersheds since about 2003. So we've been able to look at how much stream bank erosion has happened and then how much down cutting has occurred within these channels. And we find that the channels were in size like prior to development, and they're continuing to widen and deepen after development has ended, which might be related to that increase in peak flows within the watershed. It's great to have this like really detailed information about one site, but we wanted to look more broadly across, a whole watershed. So we have repeat airborne LiDAR data that we can look at changes over time within the whole watershed. So this is showing a hill shade from a digital elevation model within the watershed in 2013. And then we can look at how much changes happened since 2002 before development happened. So you can see how much the landscape was changed to, grade the landscape to make room for roadways and houses. And we can actually look at, differencing those 2 DEMs to see areas that were filled in, which is the brown areas on this map. So you can see streams and springs that were buried due to development, and then also areas that were excavated to flatten the hilltops to make room for the houses, and we can try to estimate the total amount of earth that was moved across the whole watershed using these types of data. And then lastly, I wanted to kind of give you a sense of what's happening in the streams themselves. So that's what the county was most interested in, was trying to preserve the biotic integrity of the streams within this area, because they're were deemed to be pretty high quality and sensitive habitats before the development ended. So they wanted to try to promote development that minimized the impacts on the actual benthic community within the stream. So they've been monitoring the benthic macroinvertebrates within the stream over time, so we can look at how something like the index of biotic integrity has changed over time. So this is just going to show you a series of different plots here. Any numbers that are higher indicate a healthier stream, and lower numbers indicate poor scores. So we can look at the forested site and the urban control site, and the forested site has remained in good to excellent condition over the whole monitoring period, whereas the urban control site has remained in fair to poor condition. And then we can look at changes over time as these watersheds underwent development. So the gray box in these figures shows that timing of development. So this is before, kind of when the development's sort of starting. You can see all three of the treatment watersheds are in good condition. And then as development progresses, you see a drop in those benthic scores during construction within the treatment 1 watershed. But then it sort of rebounds to good condition at the end of sort of the phase of development, and the treatment 2 watershed kind of starts to become developed and then starts to degrade during that construction period. You can see kind of the land cover changes that are happening at that same time, and has kind of remained in poor to fair condition after development. And then the treatment 3 watershed, which is just starting to undergo construction, is still kind of bouncing around, but has fallen into the sort of fair condition in the more recent years. So just to summarize here, some lessons learned from using this sort of distributed stormwater control, that this type of stormwater management can attenuate peak flows and runoff volumes, but the storage capacity within those practices really matters, and we can see differences in the performance of those events based on how long ago the previous rainfall event had happened. They can also improve water quality. We've seen reductions in sediment export within these watersheds in one of the watersheds, but we don't see those benefits for all constituents, particularly salt in these watersheds. And that it can reduce the impacts on biota, but the sensitive families haven't been able to recover in these streams. Even though you're seeing kind of a rebound in those benthic scores, the sensitive families still are in pretty low abundance in these streams. And that distributed stormwater control isn't always better if you have more impervious cover. So you need to think about trade-offs between allowing more development within the watershed, but also creating more storage to go along with that development. And then lastly, we found that the construction phase is pretty important in sort of triggering some of these impacts to the watershed. This is a time period when you see substantial changes in the topography and kind of how the flow paths within the watershed get messed up and moved around within the watershed. And we also see an increase in fine sediments within the stream channel during the construction phase. So even though there's sediment and erosion control practices, going along with construction, we're still seeing the impacts of that construction in the stream channels downstream of that disturbance. So that's all I have. If you want to know more, chat with me. Excited to talk to you more about this, and thanks so much, and happy to take questions.
Questions? Okay.
Any temperature data? Any temperature data?
We do have some temperature data. We haven't actually analyzed it yet. So we're actually trying to incorporate that into a model to try to look at how these different stressors are kind of combining sort of the combined impacts of them on the benthic community. So I'm going to come in my office to try to incorporate temperature actually, but I haven't looked at anything yet.
Any more questions?
Have you looked into the characteristics every watershed in terms of a slope, average slope, or channel slope? Because that can be, a very good factor, actually.
Yeah, so we actually see some impacts of differences in slope, especially with the cross-section data. We can, make longitudinal profiles through the elevation model, so we can see how slopes vary in the channel and also like across kind of the watershed. You see increasing slopes due to the grading and construction, and just kind of a rerouting of like where the slope has been going. We have really detailed information about how all of these different stormwater practices are connected with site network and the storage and individual facility as well. So we're hoping to kind of integrate some of that information to better understand the differences that we're seeing between these different cross sections. Yeah, we can look at slope, but definitely see higher slopes in this area, especially in the roadways.
You mentioned the base load increased over the development period. What's the reason?
That's a good question. So,
it's an impervious. It's hard to imagine the infiltration surface has come down.
Yeah. So one factor that I think is kind of related to that is, so we're seeing like longer falling limbs within the hydrograph, and those kind of remaining elevated afterwards. So that might be one reason. The stormwater practices, all of them are supposed to be kind of infiltration focused, but they all have like under drains. So a lot of that water is like that.
These soils are clay. These soils are clay mix.
Yeah. So it's we mostly looked at the treatment one watershed, which we have kind of the longest stream flow records. We're curious to see like if we see that increase in base flow in other watersheds over time, and if that base flow remains stable, like for how long. We kind of see that also sort of related to the construction as well. So like what's being counted as base flow is also including when they pump out the sediment ponds. So you can see that in the stream flow record, and that's being included as base flow, which we should use that. But it's a time period when there's no rainfall and the stream
It's not leaking water line.
is that?
It's not leaking water line.
No, it's not. As far as I can tell.
Well, thank you again, Krissy. I look forward to being able to see your presentation online later, because I really didn't get a chance to see it. And now we have Matthew. We found his presentation, New Wave Information.
Right, I guess there's more pressure on me now that I have to go last, but we'll try. Yeah. So yeah, my name is Matt Scalora. I'm a lead meteorologist at the National Weather Service Forecast Office in Wilmington, North Carolina. I'd also like to recognize Mark Willis, the meteorologist in charge at my office, as well as Darren Wright from Weather Service headquarters in Silver Spring, Maryland, for definitely being greatly involved with this project as well. And you can see there, it's going to cover the new wave information included in the NWS Coastal Waters Forecast, which I'll commonly refer to as the CWF in the talk. And in terms of all the folks that went into this work and this project itself, there's definitely a lot of contributors, over a couple dozen people on the National Weather Service National Wave Team, with representation from all around the country, every coast, and even a couple folks from the Hawaii office as well. So before we get into how we're inserting the wave forecasts into our products themselves, let's take a basic overview of waves. Waves have three very fundamental variables, that being height, period, and direction. Height is the distance from the crest to the trough of the wave measured in feet. And direction is where the waves are coming from, sort of like what we do with winds, not where it's going to. And period, definitely one of the more important variables that we measure in seconds, is the time it takes for two successive crests or troughs to pass a fixed point in the ocean, and that could be, for instance, a buoy or some other standalone object. And it's very common to have coexisting waves at any point in the ocean, and that can be near shore, it can be way out in the ocean, and all these locations are going to have unique height, period, and direction. And each of them will likely be interest to particular marine groups. In the next couple slides, I'll give you 2 examples of that. And for the time being, in our coastal waters forecast, we're definitely oversimplifying the forecast by just providing a significant wave height. Significant wave height being the highest 1/3 of all waves. So we definitely like to add that wave detail value because we think that providing it is definitely vital for mariners to decide if it's safe to venture out on any given day. So 2 examples to start off here. Currently, we're just providing a forecast saying seas 8 to 10 feet. Even though the picture looks a little taller than that, you get the general idea is these are big waves, so a big boat might think that's all right, they can handle it. However, if they saw a period forecast of 22 seconds, they might realize that a period that long is going to generate some really high surf heights and breaking wave heights along the coast, and that's going to definitely pose a shoaling hazard, especially in and around inlets. So that's something to keep in mind, and that's the value of adding this useful period into the forecast. Now, on the other hand, with smaller boats, right now we're just saying seas 2 to 3 feet. So someone with a small boat might think, oh, that's not that bad. But if they're getting a period forecast of only 3 or 4 seconds, they might realize that with that small bottom boat, the seas are going to be quite steep and choppy, and it can also pose a capsizing hazard too. So in general right now, can you imagine if we were providing a wind speed forecast but no wind direction? For instance, there are just winds 20 to 30 knots, or just providing a daily temperature forecast instead of the highs and lows that we're all accustomed to. There's fundamental components of every forecast, and in terms of waves, that's height, period, and direction to help produce a full, complete picture of the sea state. And again, leaving this information out in favor of just showing significant wave height is, again, oversimplifying the sea state. A lot of times on the East Coast, especially in the fall, you could have a north or northeast wave behind a cold front dropping through, while at the same time there may be a distant tropical system leading to a southeast swell. On the West Coast, a somewhat similar situation. We have a shorter period wave around a subtropical high leading to northwest or north waves, and again, a distant tropical activity or a non-tropical storm, a strong one nonetheless, leading to swell in all sorts of directions along the coast. And this is also a big issue for the Hawaii office as well, where they can get hit by swells in pretty much any direction in addition to their typical east to northeast trade winds. So what about the terms wind wave and swell that you may have heard of? Wind waves are just local waves that get big when you have strong winds over a large area for a long time, while swells are waves that have left their fetch generation area. And the tricky thing about that is it's kind of uncertain how long ago it left that generation area, and that can definitely affect the period. So the terms themselves are sort of ambiguous, both within an office and with neighboring offices, because there's no direct cutoff from going to one term to the next. So we feel going forward it's better to just leave the wording out themselves and just focus on height, period, and direction for simplicity, and also to provide more complete information. And now with the NWPS, which is our National Weather Service Nearshore Wave Prediction Center system, it gives us a leg up because it's providing high-resolution wave forecasts, offer forecast winds in GFE, GFE being the graphical forecast editor that we use to create our forecasts, and the WW3 boundary conditions that hopefully one day move over to more of an ensemble approach. But regardless, we're getting height, period, and direction for potentially up to 9 wave systems at any point. Typically, we only have 2 or 3 along the Atlantic coast, but the capability is there to view more data if the model is showing it. So now let's take a look at the proposed format going forward. Right now, at least along the East Coast, we're mainly just providing a forecast seas 5 to 7 feet. Some of the offices on the West Coast are also adding wind waves 5 feet and southeast swell at 2 feet. But again, I talked about the ambiguity with those two terms. And also, it's not providing a direction or period for both of those cases. So we want to transition over to including wave detail northeast 5 feet at 5 seconds and southeast 2 feet at 13 seconds. So it doesn't necessarily even lengthen the statement too long, but it's adding some more useful information. Taking this piece by piece, the first part there sees 5 to 7 feet. That's the significant wave height. Again, it's the highest average of 1/3 of all waves. And the range is optional, but in general, we kind of favor using ranges because over a 20 nautical mile zone, the waves could be a lot larger out 20 nautical miles than near shore. So giving a range is a more complete picture. But there are cases where if there wasn't much variability, meaning the standard deviation was small, that we could just go with one number. Occasional waves are optional too, and probably more necessary if you had a higher significant sea height, but it shows there occasionally to 9 feet. And that's the average of the highest 1/10 of all waves. And there's an example where it's shown, but it's up to the office to decide whether they want to include that for now. But much of the time when you have smaller waves, it's probably not that necessary because you won't get too big of a difference between the significant and the occasional seas. Now the wave detail terms, we have two wave systems there, the first one being northeast 5 feet at 5 seconds. That's the first wave system, and note that all the combination of two wave systems are scanned to potentially combine because we do want to shorten the wording if possible. So if they did have very similar period and direction, we could use the Pythagorean theorem to just combine them. So say one was 3 feet and the other was 4 feet, we could just come out with 5 feet total. But in this case, and the vast majority of the time, we are going to have separation. In this case here, just two separate wave groups. And the wave systems are ordered by their energy. Wave energy is measured by height in meters squared times period in second. And the highest goes first. And there's that second wave group, southeast 2 feet at 13 seconds. And again, if there's only one wave system, you would just include that. But if there is a noticeable one, like 2 feet at 13 seconds is fairly decent, we are going to include it. But the capability is there to actually go up to 3 or 4, depending on if the office chooses to utilize that feature. So right now, this is sort of an experimental product for 1 year. The way it works is the Weather Service issues are operational CWF as normal there on the left, and that sets off a series of internal scripts that create this experimental wave detail CWF there on the right with the wave detail version included. And it allows for a side-by-side comparison on a local web page, CMS page at all the offices, so users can easily compare the difference before and after by just scanning over one or the other. We create our forecasts in the office with something called a formatter, and this is what the output looks like on our end before and after. And you can see, again, it lengthens the product a little bit, but not significantly, but it is adding that useful information of wave detail terminology. The wave detail output has also been known to help us with our area forecast discussions in terms of the marine discussion, and also can potentially be useful for the surf forecast we issue as well, and situational awareness too. Before this experiment went national, we had a local experiment for a year. We issued a survey and had some recent partner feedback with that. Question here was, do you prefer the current version of the coastal waters forecast with no wave detail? 90% said no, meaning that they prefer the new experimental version. And just one great quote here from the Coast Guard. They said, "We can adjust our operations to match Plan Cs, and the direction and period would matter if we were deploying smaller vessels. How we would anticipate setting the ship up for deployments and similar plans. Do we drive into or with the seas? And how would that affect recovering someone in the event of an emergency?" So I mentioned again that this is a national experiment. We have participants from all around the country. Just about everyone along the Atlantic coast is involved, a couple offices along the Gulf Coast, a decent amount of participation too along the West Coast, and then the Hawaii office is involved too, even though they're not shown on the map. Social media has also been a great way to get the word out about this and raise awareness. These are, for example, images we posted on Facebook, Twitter, Instagram. Again, not just for awareness, but also to give a notification that we have a survey going out that the public can feel free to participate during the one-year experimental period to solicit feedback. And that can be viewed pretty much by anyone at weather.gov/marine/wave detail. It asks a host of different questions. And we definitely appreciate the feedback because it'll help us evolve the project and improve things before it could potentially become operational in a year. So thanks a lot for listening. I'm willing to take any questions. Yeah. And thanks for the IT help too with the getting the talk up. Appreciate it.
Yeah, thanks. It really does feel good.
So do you reckon the Coast Guard captains probably looked at wind direction with the wave information and made some of those choices out of their experience and, of doing this, but now maybe this will give them all that one thing? Like it seems like the captain was asking a question, the reviewer saying, well, what do I do with this?
Yeah. Yeah, it was helping him understand, because that'll give him the ability to do it. Now, I mean, the product itself is experimental, so we can't go on our webpage and view it in an operational sense. But if he has that link, he can address those concerns now because it'll show all the period and the wave directions compared to what he's probably used to been seeing for years. So it's definitely a little bit of an adjustment, but feedback like that definitely helps.
Yeah, that's a really good point you brought up. And I think highlights one of the reasons why we're doing this, because I think there's just for, say, a new boater, not the Coast Guard, they might think that the wave directions are going to be identical to the wind direction. And a lot of times it is, and one of the waves is, but what about that storm that's 400 miles away off to the northeast? What about the hurricane that's 1,000 miles away to the southeast? All those are going to be generating distinct wave systems. So that's what this project is allowing us to do, to articulate that information so we give the full picture of the sea state. So thank you for bringing that up.
Yeah. It's going to help all sorts of users. It's not just Coast Guard government, it's also your standard boater with a small boat too. It should help them too. So.
You think I'll go inside with two boat visits?
Yeah.
I'm sorry, until you call me the other day on the day side, if you do the end of the storm.
Yeah.
I was just going to say, do you think you mentioned a few times that you could do more than two wave systems. Do you think there's a threshold though that trying to provide that information over two systems would get confusing? I mean, like if you started tacking on more and more, people thinking about all these interactions, whether or not that's too much.
And that's a good point. And actually along the East Coast, we've capped it at 2 wave systems. But out west, since they're more likely to get multiple swell groups at once, they requested to have up to 3 groups. So the way the software is set up is you can kind of choose locally the maximum amount of wave systems you want to include. And the other thing is you can choose the minimum height you want in the wave system. So say like you're getting at, there's too many, there's like 4 or 5 groups, but the last couple only are showing 1 foot in height, and you're not really worried about those. You can cut it off at 2 feet too. So there's definitely some configuration allowed, but yeah, for the East Coast right now, we're kind of capping it at 2 groups, so.
And then I have another question, if that's okay.
Yeah.
So do you know if there's a plan for like the post-processing models that happen after NWPS, like rip currents and wave run-up, to start using the partitioned information, or still just sort of force those post-processing ones with 1 significant wave height?
Are you talking about the is it RWPS, the next software coming after NWPS? I believe it's still going to include all the wave system information. So it's just going to come a little more timely, and the resolution might be a little bit better, but I haven't heard about them removing height, period, and direction, at least for the wave system. So, but we'll see what it comes with. Yeah.
Any other questions? I don't see any online. It sounds like it's going to be really great, helpful information, and it would be possible, or maybe it will be possible to include a tiding or something like that in our Coast Watch magazine to help spread the word when the product is actually out. So thank you, Matt. That was very helpful. Let's give him a round of applause. And just a quick thank you to all of our presenters and all of our participants. It was really great to have everybody here for a couple of days. I want to thank you all for what you do individually and for coming and sharing and engaging with us. Looking forward to our next conference in a couple of years, I guess it might be. But it's really great. Thank you for all of you for being here, and have a nice afternoon.